Hey guys, welcome to our Embedded Systems 2 final project live demo by me, Asif, and Parth. Here's our PYNQ board running connected via Ethernet to the actual laptop, and here's the overview that Parth will give about our project.
Yeah, so just a brief overview. Our first step is to use a tool called Brevitas to take our .ONNX model, which is our actual image classification model, and then turn it into something that the FIN compiler can actually understand, which is FIN ONNX. Then we want to streamline the model such that we can get rid of the floating point weights and then turn them into integer weights, and then get rid of subtraction and division and turn it into addition and multiplication. So it's more friendly for the hardware, and the hardware can do computations much faster. Then we turn those specific instructions into hardware layers, and in these hardware layers we have specific RTL nodes, and then we want to specialize the layers to our actual board because we have certain RTL, but we need to map this out on the actual FPGA. So we have the PYNQ Z1, so we want to specialize those layers to that specific PYNQ Z1, and then generate a bit stream, and then create some stitch design that will have a bit stream already loaded in. But these are the chunk of codes that actually do these operations. So Brevitas, this is turning this into something that's FIN compatible. We have network preparation. We have post and pre-processing on the model that we have to do, and the streamlining that we're going to do, which is going to change these operations, and the hardware layers, and then finally all the way at the end we have the actual creation of the RTL, and then we have parallelism here, which can indicate whether we want to use parallelism for the actual execution of the instructions. And then finally we have the actual hardware built and the generated outputs, where you have these are all your RTL nodes.
Nice.
And then finally
Show them the terminal, the project.
Oh yeah, so this is our actual hardware project. So the actual compiler takes, it creates a directory where we have our XPR over here, our XPR project, and then we also have a bunch of our bit files, our bit streams, and their configuration files, and then the project files, which correspond to this specifically, this hardware design right over here that we have. And the idea is the first thing that we're going to do, the first thing that we're going to do is, so we're going to deploy this on the board, and the first thing that we're going to do is we're going to take this number 2, and then the image is supposed to be classifying this as a 2. And that's the first thing that we're going to do. That's the first thing that our model is going to do. So, then here, we'll talk more about on the PYNQ side. Talk about the PYNQ.
Yeah. So just to pick up where you left off, our goal is to classify this handwritten 2 as an actual 2 by running the model on the board right here. So if you go to the terminal right here, we are currently SSH'd into the board. So this terminal right here is the root user of the board running right here on the chip. This is all coming from the chip. So first, we just sudo rooted into this root user, and then we went into like the SSH into the Xilinx board, and then from here, now we're in the Xilinx directory. And what we're going to do first is, so we have this, as you can see right here, we have this input, the NPY. This is the file format of this handwritten 2 on the board. And now our goal is to run a script to execute it and see what the output is like. So let's do that real quick by copying this command. So this command right here, it takes as input the bit file that we generated from the Vivado project, specifies the input file input.npy, and executes a Python script, which should give us an output.npy file. These are just warnings, no problem. I think these are just like about some deprecated stuff or some old stuff. And then we should, yeah, there you go. So it ran. So now we should have an output.npy. If we ls, we have the output.npy right here. And then we can run our script. So just to show you guys what the script is, here's the script that we're going to run, loading the npy file and then printing the output. So if we actually do Python 3 script.py, it should output to us the input shape and the input. Yeah, sorry about that. So before we actually ran the wrong script, and that was just showing the input of the file, the input.npy, which is the input shape and the input data of the actual 2 that we have right here. So now we're going to run the script to actually show us what the command that what the command that we ran right here, where the resizer.bit and our input gave us. So if we run this script right here, we should get right here. So output shape 1, 1, and our output data 2, which is perfect because the output data is telling us what the model is actually classifying the handwriting image as. It classifies it as 2, which as you can see is right here. And this is again all running right from here, the board. Now, next we're going to test it on the entire data set. So we have an entire mnist data set with I believe about 10,000 images on there. And now we're going to test how the model performs in terms of accuracy on the entire data set. So this is a validated.py script that we're running. The data set is mnist because we're classifying handwritten images, and our batch size per each iteration is 1,000. So we should have total 10 batches. Let's give it a second to run. These are the same warnings from earlier, doesn't matter. And there we are, perfect. So we have, here's our 10 batches, total of 10,000, and our accuracy was 92.96, which means our model classified with a pretty high accuracy. And I think our target, from what I remember, was 90. Yeah, so our very close, our actual report is 93.17, and we were able to achieve a 92.96 by running it on the board, which is pretty good. And next, we're going to do a throughput test on the PYNQ board. So that is this command right here, which will tell us how well the model is actually performing in terms of like operations and computations on the board. And so again, we're going to run that resizer.bit file. We're going to put the bit file on the board and run this command, the driver.py, which tests the throughput of the model on the board. And any second, here we are, perfect. As we can see, results ran to the nw.__metrics txt. So if we open up this file and read it, here we are. So our total runtime for this entire data set, 10,000 images, was 1.32 milliseconds. And our throughput of image per second was 753,693 images per second. And we have our DRAM, our DRAM in, our DRAM out, our clock frequency, our batch size per, which was 1,000, and then other stuff like, you know, input data to device, output data to device. Sorry, this is the runtime for this script, not the script above. This is the runtime for this script. And yeah, that was honestly really solid. That's a lot of images per second. And so as we can see, the model's performing really well on the actual board. And yeah, thank you for your time.
Thank you. Bye.